Madam, for the invitation. So Game and I will talk on central theme in theory of random graphs, which is basically random graphs with a given degrees. And in particular, we're going to focus on my talk at least will focus on percolation on these random graphs. And actually, my talk will focus on what we call sparse random graphs, whereas Guillaume's talk will look at more dense degree sequences. So basically. What is the theme of this talk? The theme of this talk is as follows. So we have a given degree sequence, and we select a graph uniformly at random among all graphs with this particular given degree sequence, and do bond percolation on this random graph. Okay, so in particular, for us, the vertex set will be the set of numbers 1 to n, and the associated degree sequence is denoted by d subscript n, and these are the degrees, d1 up to dn. And the meaning here is that vertex I will have degree di, and obviously this should satisfy some feasibility conditions, such as, for example, if the sum of the degrees is even. And as I said, a graph is selected uniformly at random among all graphs with this degree sequence. And percolation then is performed on this graph, meaning that every edge of this random graph GDN is retained independently with some probability P, which possibly depends on n. And the general question here is, what is the component structure of the resulting graph? Okay, so what I'm going to talk about today is joint work. It's based on joint work with Felix Joos and Guillaume that dates back to an era where both Felix and Guillaume were here in Birmingham. But now let me start with a bit of history of percolation theory. Percolation theory actually started in infinite graphs. So it was the paper by Broadbent and Hammersley in '57, which introduced the percolation model. So look at the d-dimensional integer lattice. And in this infinite graph, every edge is declared open with some probability P. Of course, there's no n here for P to depend on n, and this declaration is independent of any other edge. And if LD is the d-dimensional lattice, LD with subscript P is the open subgraph of this, which means that it's the graph that contains only the open edges. And the question in this context is whether there's an infinite open path starting at the origin. Okay, so suppose that C is the connected component of what remains in the percolated graph that contains the origin, and theta of P is the probability of the event that the order of this component is infinite. And a central result in this context is that there is a critical value. Indeed, there is a critical value PC depending on D, such that this probability is 0 if P is less than this critical value, but is positive if P is bigger than PC. And for example, for D equals to the two-dimensional lattice, it was proved by Kesten in 1980 that this critical probability is a half, and that was already a non-trivial result, and it was an open problem for a couple of decades already then. So this is a general context of percolation theory. As I said, started in the context of infinite graphs. So in that context, one would think of this as basically the immersion of some porous medium into a liquid, and the question would be whether the center, for example, of this porous medium would receive some of this liquid. And the porous medium was effectively modeled by this random subgraph of the d-dimensional infinite lattice. In our context, though, we do not do percolation on infinite graphs, but we consider this process on finite graphs, in particular on sequences of finite graphs, Gn. So we will assume in general, unless otherwise, I mean, unless not the case, I will state it. The Gn is a graph on this set of vertices, numbers 1 to n. And the assumption is that Gn is connected, or at least has a connected component that has order proportional to n. And as I mentioned in my introduction, on Gn, we consider this random subgraph G subscript P of Gn, where we retain every edge independently with probability P that's a function of n. And the question, I mean, as I said earlier, what we're interested in is the structure of the remaining graph, and in particular, the question that we're going to address is whether there is a C such that with probability that tends to 1 as n goes to infinity. So here, instead of looking at infinite graphs, as I said, we will look at finite graphs where the order n goes to infinity. So the question is, if there is a C such that with probability that tends to 1 as n goes to infinity, the percolated graph, the remaining graph, has a component of order at least Cn. That is, a component that contains at least Cn vertices. So this statement, the probability tending to 1 as n goes to infinity, we abbreviate as with high probability WHP, that is. Now, a component like this is commonly referred to as a giant component. And going back to my assumptions, this is why basically I assume that the graph we start with is connected, or at least has a component of order proportional to n. Okay, because otherwise the question is trivial. But of course, in that case, one could ask different questions about the order of the largest component and so on, but we'll not discuss that here. Okay, so this basically is a theme that has been studied since the beginning of the theory of random graphs. So already the binomial model, GNP, introduced by Gilbert in the late 50s, can be viewed as percolation on the sequence Gn, where Gn is now the complete graph on n vertices. Okay, and this is one of the standard models, with the classical models in the theory of random graphs. And indeed, in this case, there is a critical value for P, which turns out to be 1 over n, such that if P is slightly bigger than 1 over n, so 1 plus epsilon, where epsilon is some positive constant, then with high probability G, P, the percolated graph has a unique giant component. And in fact, every other component has the most logarithmic order. But on the other hand, if P is slightly less than 1 over n, 1 minus epsilon over n, then with high probability, all components are of logarithmic order. This is a result that was one of the classic results of Erdos and Renyi that were proved for an almost equivalent model, the GNM model, with a given number of edges as well, but was refined later by Bolobas and subsequently by numerous other authors, and studied in great detail later. Okay, I mean, like what happens at the phase transition, the critical window, and so on. Another example is to take Gn to be the n-dimensional hypercube. So here we don't have graphs that have like where Gn has n vertices, but n here is the dimension of the hypercube, meaning that Gn has 2 to the n vertices, and has been proved by Erdős and Spencer, and completed by Attai, Komlos, and Samaredi, that again 1 over n is a critical probability for the appearance of a giant component if one does perform percolation on the n-dimensional hypercube. Okay, remember that n here is a dimension, not the order of the graph. So Erdős, I think, Spencer proved the lower side, and then that was completed a couple of years later by Attai, Komlos, and Samaredi, who proved the upper side, the 1 plus epsilon over n. Now, later, Nogallo and Benjamini and Anastasia consider sequences, like more general graphs of graphs, again, on n vertices that are expanded graphs and have bounded maximum degree. And they showed a number of results. One result shows that if one performs percolation on such a graph with probability p that in general depends on n, for any there exists an omega such that the percolated graph contains at most one component of order at least n to the omega. So if there is a giant component, you'd expect at most one. You'd expect one giant component under these assumptions. And another theorem in the same paper is about the case where Gn is a deregular expander graph with high girth, a girth that tends to infinity as n goes to infinity. So let's recall that the girth is the length of the shortest cycle in the graph. So in this case, they establish the 1 over d minus 1, that is 1 over the degree of the regular graph minus 1, as the threshold for the emergence of a giant component. So in this case, they proved that if p is bigger than 1 over d minus 1, then with high probability, the percolated graph has unique giant component. But this is not the case if p is less than 1 over d minus 1. And in particular, this implies that 1 over d minus 1 is the threshold if you select a Gn as a deregular random graph on n vertices. And that was a result that was proved by Andreas Gert a couple of years earlier for random regular graphs. And in 2008, Boris Pidel refined the analysis and looked at the critical window in this phase transition. And now, of course, a deregular graph can be viewed as a graph with given degree sequence where every vertex has degree exactly k. And the question is, what happens more generally? Okay, if we have a sequence of degree sequences, like I described at the beginning, so the vertex Z is a set of numbers 1 to n, and vertex I has degree di. And in this talk, we're going to focus on the case where this degree is distribution is sparse, meaning that the average degree is bounded. Okay, so this is what we mean when we talk about sparseness. So first, the question is, if we take GDN to be a random graph with a given degree sequence, does it have a giant component? So before we perform any percolation process on this, we need to know whether it's meaningful to do so from the point of having a giant component. And it was a theorem by Mike Molloy and Bruce Reed proved in the 1990s, and two papers in RSA, random selection algorithms, and in CPC, where they gave a characterization of on the degree sequence, which leads to with high probability existence of a giant component. Now, as I said, we considered a sequence of degree sequences. Okay, so dn, n goes to infinity. We'll look at the number of vertices of degree k. We denote this by dn sub k. And let us assume that the fraction of vertices that have degree k as a fraction of the number of vertices tends to some constant lambda k, and this constant does exist. And suppose that these constants lambda k satisfy this inequality, namely that the sum k times k minus 2 times lambda k is finite. Mike Malloy and Bruce Reed proved that under certain set of assumptions, primarily having to do with the maximum degree, is the quantity q, or the sign of the quantity q, that essentially characterizes the with high probability existence of a giant component. So basically, they proved that under this assumption on the maximum degree, if q is positive, then the random graph with this given degree distribution has a giant component. But if q is negative, then this is not the case. Okay, so basically, we get a largest component that is that's sublinear. Now, this result was looked at from several directions. So firstly, Mihan Kang and Charles Arstad, and later Hatami and Molloy looked at the near critical, the critical window. So what happens when q is at 0, close to 0. And the other direction of research, the other line of research, was to try to understand what happens if we drop these conditions, particularly on the maximum degree, and also on the existence of limits, limiting distribution on the number of degrees of the number of weights of degree k for all k. Now, that second line of research was pursued by Svante Janssen, Malvina Luczek in 2008, and later by Bella Bolobas and Oliver Jordan, who relaxed these conditions, basically on the maximum degree, although some conditions on the maximum degree are implicitly in their theorems. But now, let me try to explain intuitively why this q is the right quantity to look at, and why does the sign of q determine the existence, the emergence of a giant component. So basically, q was defined like this: it's the sum of k minus 2 times lambda k over all k at least 1. So this is equivalent to saying that the sum of a k times k minus 1 lambda k is bigger than the sum of k lambda k. And if we rearrange, this is equivalent to having this sum as being greater than 1. Okay. Now, what is this sum? So basically, the sequence of the lambda k's, can be viewed as the limiting degree distribution. Okay, so essentially as a distribution of some limiting random variable, which is essentially the random variable that is the degree of a uniformly selected random vertex. Okay, so this is the lambda k, the sequence lambda k. Well, what about this? This is basically the expected value of the size bias version of this distribution. What is size bias version? So if you have a random variable x, say a non-negative integers with probability distribution being lambda k, the probability that the size bias version, which I denote by x hat, is takes value k is equal to k times probability that x is k divided by the expected value of the random variable x. So we'll make sure that these probabilities here on the left-hand side add up to 1. Okay, so basically, going back to this condition, namely this sum is is bigger than 1, essentially implies that an associated branching process is supercritical and basically gives an infinite tree with positive probability. Okay, so in other words, we can think of the exploration process as like starting from a given vertex, but not going too deeply, okay, in the graph, as a multi-type branching process, okay, where the type of vertex is basically its degree, and when a vertex of type k is selected with probability proportional to k times lambda k, meaning that intuitively vertices of higher degree are more likely to be generated. Okay, but this vertex, if it's selected, it gives birth to k minus 1 offspring because already one of one edge from the edges associated, from the k edge associated with this vertex of degree k, is attached to the vertex that has produced it. Okay. So basically, this is an approximation of the structure of this uniformly random graph with this given degree distribution at a local level, meaning if you don't go too far around a given vertex. And essentially what this result is saying is that if this number is bigger than 1, going back to Q, meaning that Q is positive, if you look at the neighborhood around a given vertex, then what you see essentially is a supercritical branching process, okay, which means that it gives an infinite tree with positive probability. But of course, in this case, we don't have an infinite tree, but the infinite tree essentially would correspond or give rise to the giant component. And on the other hand, if the left-hand side is less than 1, the corresponding branching process is subcritical and basically dies out with probability 1, finishing in a finite tree. Okay, so going back to percolation, so doing percolation on this random graph on GDN at local level is essentially like doing percolation process on the tree that is associated with this branching process. So, like in GDN itself, in the percolated graph, the percolation process gives a giant component if this branching process is supercritical. So basically, what we consider here as the Osmium distribution is essentially a thinned version of x hat, where we're looking at binomial distribution with parameters x hat comma p. And this branching process, which is basically the branching process, the original branching process together with the percolation process. So basically, when uh, a vertex produces its offspring, then each of them is retained independently with probability p, or like each edge emanating from a vertex is retained with probability p. Then this is a branching process that is supercritical if and only if this product is bigger than 1. Rearranging, we get this critical probability. And basically, this expectation, or the inverse of this expectation, is given by this ratio. Okay, so you would expect that it is this ratio that gives the critical probability for the emergence of a giant component in GDN P. Okay, and that was indeed the case, proved by Svante Jansson and myself independently more than 15 years ago. And again, the critical window was considered about 12 years ago by Oliver Riordan. And all of these papers basically come with some limitations. So basically, one limitation is the existence of a limiting distribution, okay, namely that there is some limiting sequence lambda k. There's a bounded second moment in this limit. So there are limitations about the tail of this distribution, and limitations on the maximum degree. Okay, and some of these limitations come essentially from the actual tools that one uses in order to study a random graph with a given degree sequence, which is the configuration model. The configuration model has been a classic model to, like a very standard model to study random graphs with a given degree sequence. Thing was initiated with Bender and Canfield and standardized by Bela Bolobash as a model for studying graphs with given degree distributions, but it has some limitations, and these limitations involve or essentially imply these assumptions one has to take on these limiting degree distributions and also the maximum degree. Now, going back to percolation, Bolobos and Riordan, in the paper that I mentioned beforehand, generalized basically what Svante and I had proved some years ago, keeping the assumption of a limiting degree distribution, but assuming only that this sequence of degree sequence is uniformly integrable. Okay, namely for every epsilon there is some c, so that if you look at the amount of degree that exists among vertices of degree at least c is less than epsilon. So for every c there is, for every epsilon there is a c such that this holds. And in this case, they proved that the largest component, the order of the largest component, converges in probability to some constant. Okay, and the constant actually turns out to be the probability that the associated branching process survives. Okay. Okay, so now these limitations that I mentioned were removed completely by a breakthrough result by Hughes, Perronneau, Rautenbach, and Reed more recently. In the following way, so here we don't assume that the sequence of degree sequences has a limit, okay, but we make the following assumption. So suppose that the degrees are ordered with lots of generality, so D1 is less than D2, etc. And we look at this quantity JDN, which is the minimum index, such that essentially this sum d minus 2 becomes positive, or n if this doesn't exist. Now look at the total degree vertices of index at least JDN, and look at the total degree that involves only vertices of degree different than 2. So basically, what determines the existence of a giant component is the relation between these two quantities, R and M. So they show that if, for example, R is little of M, we have some delta of n function is little of 1, then for any gamma, the order of the largest component, GDN, is at most gamma n. But if but for any epsilon, there is a gamma such that if R is at least epsilon times n, then a giant component exists. Okay. Of course, in this context, I'm not sure whether it makes sense to look for the limit of this, like of the fraction of vertices in a giant component, because we don't have this assumption about limiting degree distribution, right? So, and so in this case, this branching process approximation may not be accurate enough in this case. Although in the proof of the theorem there is some essentially branching type process involved. Okay, so now going back to percolations, so we would like to do percolation on random graphs with given degrees given by the sequence of degree sequences. So as I said before, we assume that these are sparse degree sequences, and the average degree is uniformly bounded by some constant positive real number d bar. And we consider two assumptions. One assumption is that we call A1xc. So here we look at vertices of degree at least c, and we say that the sequence has this property A1xc if the sum of the degrees of at least c scaled by n is at most x over c. And a second property, A2x with parameters C1 and C2, which is like a second moment property. And this looks at vertices of that have vertices have degree between C1 and C2. So here C1 and C2 are such that C1 is less than C2. And you look at the square of this degree scaled by n, and property A2x C1 C2 means that this sum is at most x over 4. Now, our theorem basically gives a critical probability, which is sort of similar to the critical probability I presented earlier. Okay, except that now you don't look at the entire degree sequence, but you look at essentially this critical probability is determined by vertices up to C2. So, okay, there are some complicated choice of these numbers, the epsilons and gammas and c's and so on. But let me go straight to theorem. So the first part is about the property A1 epsilon C2. So think of epsilon as an arbitrarily selected constant. Okay. And again, C2, same, is a big number. So if A1 epsilon C2 is satisfied, then if P is less than this critical probability, is 1 minus epsilon PC, then with high probability, the largest component has order at most gamma n. Okay, again, gamma is something that we can choose. So it could be any arbitrarily small constant. And for the supercritical case, we need like if P is 1 plus epsilon times the critical probability, then we need additionally the probability A2 epsilon C1 C2. So if this holds on top of this, then with high probability, the largest component is at least has order bigger than rho times n for some constant rho. It depends on C1 and epsilon. Probably gamma shouldn't be there, I think. Okay, so this is about the existence of like phase transition, so to speak. On the other hand, if these like one of these conditions, A1 and A2, are not satisfied, okay, then with high probability, in this context, with high probability, we mean probability 1 minus delta for some small selected delta. Then for any P fixed, there is a giant component. So the order of the order of the largest component is bigger than rho n. Okay, for some rho. Okay, so and this case has been labeled as heavy tail case because effectively, if these conditions don't hold for some big, I mean, if you take this x here as this quantity k big, which think of as a big number, if they fail, then this means that the opposite inequalities here hold, and therefore we have heavy tails in the degree distribution. Then heavy tails imply the existence of a giant component. Now, let me briefly talk a little bit about the proof strategy. Okay, so basically I mean, I'm going to talk about the proof strategy of this theorem, okay, where we don't have heavy tails. So firstly, with this C2, we look at all vertices of degree at least C2 and the neighbors. So we show that these involve total degree, which is small fraction of n. And basically, if we are in the subcritical regime, so if we take a P that is less than the critical probability, by less I mean 1 minus epsilon times the critical probability, then this sum here is linearly negative. Okay, what does this mean? So this means that we start an exploration process. Starting from we start revealing the graph, starting from the graph that is induced by these vertices of high degree, namely degree at least 2 and their neighbors. And so when we start revealing these vertices, and basically the vertices that we incorporate are have bounded degree. Okay, so we don't deal with vertices of high degree. And starting with this as our S naught, and we start revealing neighbors of the set, one vertex at a time, and we keep track of the expected change in the total degree. And basically, this condition here in item 2 implies, I mean, if you don't run this process for a long time, so if they think of it as a small, like basically linear, but small fraction of n, so essentially we're talking about a process that has expected change that is negative. And basically we show that with high probability stops in a small linear time, like a small fraction of n. And similarly or analogously, if P is like 1 plus epsilon times the critical probability, then the opposite condition holds. So this sum is super linear. Sorry, it's positive, but linearly positive. And this stays the same during this process for quite some time as a linear time. And basically, this ensures that the total degree going out of this set ST grows. Okay, and of course, with some more work, we need to show that then it gives us a giant component which contains at least a certain fraction of the vertices, which is given by this constant rho stated in that theorem. And from a technical point of view, the main tool that we use for calculation of probabilities in this context, and actually that was the tool that was used in the theorem about the giant component by Hughes, Guillem, Radenbach, and Reed, is the switching method. Okay, so the switching method is essentially here replaces the configuration model. Okay, and the plus side of it is that it doesn't impose those restrictions that the configuration model imposes when we use it in order to analyze graphs with given degrees. Okay. And I think I will stop here. That's all I have to say. And the switching method will be analyzed, will be presented in more detail in Guillem's talk, who is going to use it for what he's going to talk about. Okay, I'll stop here. Thank you very much.
All right, thanks, Nikolaos.